How's it going, everyone? Welcome, Elier Gonzalez here. So, today we're going to now talk of the generalized and specialized ideas around the functional programming, because this is part of the central aspect of once you know what a referential transparency means, which is the way of how you can now create is a function that is pure, aka that anytime that you call a function, the output of that can be replaced in any part of the program and it won't alter the state of it. So this is a crucial aspect of this, because especially if you're working with application, with programs, with states that you want to now reflect, and this is most of the time more visual on UI, right? When you have now a particular UI state that you want to change to another, and to another, and to another, and to another, and to another, all right? So for example, it's like you have now a particular checkout process or an onboarding process, and the way how you put all of this kind of stuff is that, hey, this is perhaps the way how you want to put is your name, and then your identifications, and then some questions, some personal questions that we need to ask you, as well as some other questions, so on and so forth. So once you now pass through all of this, so we can collect all of that data and then show you the proper product or service. Okay, so this is interesting, because all of these particular states, the idea is that by the time that you call those states or you call those functions, we wrote that in a way that it won't affect the state of the applications. So this referential transparency concept, which is something that you got it? Yeah, this referential transparency. So referential transparency is just a fancy way to say, which is the canonical and complete full definition for a pure function call, is that a function call is pure when you can replace the output value and not affect any of the rest of the program. So in other words, if you, and this is interesting. So now something in my mind make click, because by the time that you call that function, and if that function for some reason now is performing some side effects or is causing the state of the application change in an unexpected way, so by the time that that function runs and returns you something, then your application now is in a different and unpredicted state. So this is the reason why functional programming, which is a particularly programming approach, the value proposition of this is that the code is provable, because now they're relying on all of these mathematical fundamentals, mathematical tools that allows them to now have high level of confidence when they implement that in this particular way. Why this is important? Useful when you need to handle a lot of the user interface and different states that those applications can be. So it also makes a lot of sense, and also for the backend. So when you need to actually deal is with a lot of this particular state, and this state now change. So first thing first is that how you can now is design your program in a way that not only anytime that you call that function, you know that you can replace the output and it won't affect the rest of the program, which is part of the pure function concept, which is the canonical complete full definition of a pure function call. And also is that what happened when we need to, for example, apply some series of transformations to a huge collection of data, all right? And how can we now is keep up the state change in our applications so we can keep track when a particular state change. So this is again for the functional approach, because we also have some mechanism in JavaScript that allows to do that. For example, like proxy, right, where it notify us when a particular state change happened, and therefore we can run some particular functions. So, but the TLDR of this is that this is the reason why we went through all of this concept over the past, oh my God, 3 months. I will put it into 5 months. So over the past 5 months, to understand now the value proposition of pure functions, especially when you're writing your functions definition, and also for function calls, and explore now that following this particular recipe or these rules, okay, when you need to have certainty in your code, by following those recipe, you can get now this desired and expected outcome. So far, so good, right? Now, the thing here is there also are some other ideas around the functional programming, around the concept of function purity, that is generalized and specialized functions. And this is similar to when you have now this Cartesian graph, when you, for example, say, hey, I want to now fix the point in 3 on the y-axis, right? And then you can draw a line in any direction, so given x point, right? This is somewhat similar in the case of, by using now this generalization, which is something that we were describing here, okay? So by looking at the generalized and specializations, okay, this is a fun, it's a key idea in functional programming. So the value proposition of this generalized to specialized functions is that you can now see the relationship of this general purpose utility that you can define, and then now take slice or take specialized versions, specific stuff that you want to do with. So what is the intent of this? Again, it's for the author of the code, that whenever he reads that code, he knows the intent of that line of code. So we also look at this particular example. So for example, Ajax and get customers. So between the line 3 and line 9, well, line 9 is pretty much descriptive that line 3, right? So why, for example, in this another case, we didn't use the Ajax. Instead, we use the get customer. Again, because we want to see now is the relationship more clear from this generalized function and this specialized, right? So this is why, and we also look at this generalized and specialized version, because now when you're passing parameters or you're passing arguments to those functions, okay, the order matters. And the generalized functions or this generalized and specific functions, so the way you're going to pass the arguments, the order is from the most general to the specific. So that's why we look, for example, in map, that it receive first is the function and then the values of that collection. So this is something that is important to, especially if you're going to define this kind of pure functions, as well as passing is the argument. And there are 2 techniques of how you can now specialize functions. And this to me was now mind-blowing. And also the reason why we're doing this kind of storytelling, because it makes a lot of sense of what's going on. So partial application in currying and partial application in comparison. So the TLDR is that they are both specializing techniques from generalization to a specific, right, or specialization techniques in functional programming, where now the partial applications say, hey, I'm gonna pass this now a set of arguments right now, and then by the time I call that again, I'm gonna pass the rest of the parameter, which is this. So partial application says I'm going to pass a set of, or I'm gonna pass a preset argument first, and then when I call the function again, I'll pass the rest of it. Okay, so I'll pass the rest of it. I'll pass the rest arguments. The rest of the arguments. Okay, so far so good. This is great. Now, whereas the currying, which is interesting because currying is now mathematician is a computer science that call Haskell Curry. You know, Haskell Curry. Okay, is an American mathematician and logician, Haskell Curry. That now he has that. Really? They don't have image of that. Nothing is exactly Haskell Curry. That makes a lot of sense. Haskell Curry. So he invented this particular techniques, the currying, okay, in which this is the way of how you can pass is inputs to a function. Okay, so it's the way of passing single inputs, or is a way of passing inputs to a function via unity functions. Okay, so if I copy and paste this and say, hey, please now Claude help me this, okay, it's true. This is essentially correct. Partial application involves taking a function that has set multiple arguments, fixing some of its arguments initially, and returning a new function that takes the remaining arguments. You are pre-filling some arguments and leaving others to be supplied. For currying, the statement say is the way of passing inputs to a function via unity function. This is also correct. Currying transforms a function that takes multiple arguments into a sequence of functions. And I prefer to use this terminology here. Okay. So partial application involves taking a function that has set multiple arguments. In other words, taking a function. Okay. In other words, taking a function that has exact is to in other words, taking a function that has so taking a function that has had multiple arguments, exactly. In other words, taking a function In other words, taking, in other words, Jesus, is a function that takes some of the arguments first, and then on the next call, and then returning a new function exactly. Because this is more technically, but to be more to be more clear, to be more on the street, to be more crystal clear, is that I'm going to pass now a preset of arguments or values first, and then call the function again, and pass, and then call, and when I call the function again, pass the rest of the arguments to that function. So in other words, it's a function that takes some of the arguments first, and then on the next call, okay, and returning a new function that expect and return a new function that takes the rest of the arguments. This is pretty simple. And the other is a way of passing inputs to a function via unity functions. In other words, is a function that receives its input as a sequence of functions. And I love about this. Current transform a function that takes multiple. Okay. In other words, it transform a function to receive so it transforms a function to receive its input as a sequence of functions, each taking a single argument, the unity function. So yeah, it's not that hard to understand that. In fact, it makes a lot of sense when you see at least some of the application now. Your knowledge will be tested when you need to apply that in real life.
In terms of our Ajax function, there are two line of Haskell. That's all Haskell. So if you want to pass in 3 inputs, what do? You have a curried function that takes them one at a time. As we go along, a partial application of getCustomer. So that partial utility allows me, each time I call it, to preset one or more inputs and produce a function which is expecting all the rest of the inputs. That's what partial application is. Partially applying some of the inputs now, receiving all of the inputs later. You'll notice that to do a 2-stage specialization like I did, I had to call partial twice.
Partially
you see that?
Applying.
I had to call partial once, and then I called it a second time to make the get current user.
And then later on. And then the rest later on.
Partially applying some of the inputs now.
Except they partially apply the arguments or some of the inputs now, and then the rest.
Receiving all of the inputs later.
And receiving the inputs later. Okay.
You'll notice that to do a 2-stage specialization like I did, I had to call partial twice. You see that? I had to call partial once, and then I called it a second time to make the get current user. That's one way of doing specialization, is called partial application. Another way, which quite frankly is much more common within functional programming, you will tend to want to do partial application as you get started, and then you'll find out actually everybody does currying. Okay? And you'll see why as you go along, as we go along in the course and as you get more practice with this. But currying is the much more common form of specialization. I used to tell people, and many people have said this before, I used to tell people that currying was a special form of partial application. I now would describe them more like cousins. They both accomplish the same end goal. They both specialize a generalized function, but they go about it in a somewhat significantly different way. So let's look at currying. Back to our Ajax function. What if I wrote the Ajax function like this? Okay? It looks a little bit different because I have this 3 levels here. I have an Ajax actually calling the, I'm expecting the next annual curry. Slide we'll see an intermediate function. That's how we get the specialization. If I call Ajax with only customer API, I get back a function which could be called getCustomer. The function on line 2 is essentially getCustomer. Use your equational reasoning and you'll see that they're basically the same thing. And then if I call the getCustomer with the data, what I get back is getCurrentUser. So you'll see the same specialization just as we were doing on the previous slide, but now notice that I didn't have to call like a utility every line. All I had to do to get the more specialized function was just pass in the next input. Pass in an input, get a more specialized function. Pass in another input, get an even more specialized function. And you keep doing that, you keep getting a more specialized function every time. This is a technique called currying. Where does that come from, by the way? The Haskell programming language. Everybody knows or probably has heard at some point or another about Haskell. I don't really know anything at all about Haskell. I can literally write 1 line of Haskell. That's all I know about the programming language Haskell. But what I know is that one of the co-inventors of Haskell, his name was Haskell Curry. He invented this technique of currying, or at least co-invented this technique of currying. We call it currying because it is essentially the way that all inputs go into functions in Haskell. So in Haskell, you don't write like a binary or an n-ary function. There's no such thing. All functions are unary in Haskell. So if you want to pass in 3 inputs, what do? You have a curried function that takes them one at a time. There's no such thing as pass all 3 all at once. Kind of thing. So currying comes from this idea of if I could only pass in 1 input at a time, how could I make multiple inputs go into a function? Sometimes my function needs multiple inputs. Now, this is doing it manually, but it would be nice if, for example, we had a utility that could do that for us. And indeed, we do have a utility that can do that for us. By the way, in the commented lines, you'll notice that I'm reusing the arrow function syntax. Line 1 is the traditional way that that is written out. And that you'll see URL and then the fat arrow. Let me highlight this for you. You'll see URL here. My highlighter will overwork.
Completely, man.
There we go. URL, and then the arrow, and then data, and then an arrow, and then CB, and then an arrow, and then whatever the function needs to do its work. Okay? That's that 3-level nesting. It's just written all in one line. And a lot of functional programmers really like the arrow function syntax because this arrow function syntax is almost identical to the mathematical notation and the Haskell notation for a curried function. That's why they love writing it in that style. I am decidedly not a fan of arrow function syntax, which is why you haven't seen any arrow functions on any of my slides. I'm not a fan of that syntax, but if you absolutely must do this chained arrow currying thing, please do line 2. Do a favor to the reader and at least wrap parentheses around each function boundary. Just slightly more not so crazy on the readability, okay? If I can't convince you not to do nested arrow functions, please at least wrap your arrow functions in parentheses, your nested arrow functions in parentheses. Okay, arrow functions aside, in JavaScript, we can define a utility, and indeed, all functional libraries will provide you a utility. It's often called curry. Sometimes they'll have a variation of it called curry n, meaning like how many I want to curry. It looks like this. You call curry, you tell it how many inputs you're expecting to receive,
Processing, bro.
and then you provide it a function. And notice that this function here doesn't have to be manually curried. It's a regular old normal function that's expecting some n number of inputs. This curry utility automatically adapts it into being that unrolled thing that's going to accept 1 input at a time. In other words, it creates a wrapper adapted function whose job is to keep returning a new function that expects another input until you've provided the specified number of inputs, and then it calls the underlying function with all those collected inputs. And that gives us the ability, line 7, to call Ajax with the URL and get back a getCustomer function, and then call getCustomer with the data object and get back a getCurrentUser function. So you'll notice that we have the same outcome with curry as we had with the partial application. We just got there in a decidedly different way. Same outcome, which is that I have a general function AJAX, an intermediately more specific function called getCustomer, and an even more specific getCurrentUser. But with partial application, if you were to look a couple of slides back, to get each level of the specialization, I had to call the utility again. With currying, I call it once at the beginning to set up my function, and then it automatically specializes itself as I pass inputs. And I think that's one of the reasons why currying is more attractive, is it ends up being that you write fewer calls to these utilities. You call it once to set up a function, and then you just automatically can specialize it. As a matter of fact, virtually all functional programming libraries that you will encounter, all of the methods on those functional libraries are automatically already curried. Because it turns out functional programmers want everything to be curried. And if you remember what I said at the very beginning when we were talking about shapes, one of the reasons why functional programmers like curried functions is because they like unary functions. Single input, another output. And you can see that a curried function is exactly that. It is a chained series of unary functions. Single input, single output, single input, single output, single input, single output. So in other words, to summarize this partial application versus currying thing, what we could say is that they are accomplishing the same thing, but doing it in a different way. Both of them are specialization techniques. Partial application is going to preset some of the arguments at the beginning, and then receive all the rest of them on the next call. And if you want to do multiple steps of that specialization, you've got to keep calling the utility. Currying, on the other hand, doesn't preset any of the arguments, and it receives each argument one at a time. If you ever get asked on a future job interview, what's the difference, what's partial application and currying? The answer is both of them specialize. They do it differently. Partial application takes some input now, all the rest of the input later. Currying takes no input now, each input one at a time. By the way, I want to back up real quick, one slide. Skipped over one thing I didn't want to skip over. There is this notion of what I would call strict versus loose currying. And I'm calling this out because you're going to encounter this, and you may ask yourself. This idea that I've been showing you with currying has been like we see on line 7, which is that each time I call the function, I provide only one input. Because that's how we did it when we manually curried. That's how it works in Haskell. You provide one input at a time. I would call that the canonical or strict interpretation of currying. But if you had a function, say something that received 5 inputs, and you knew 3 of them right now, and you wanted to wait to define the other 2, you can see that it would be a little bit annoying to have to do 3 separate function calls with 3 separate parentheses. It might be much more convenient, like line 10, to just be able to provide 2 inputs all in one call. You see where I'm coming from? So that technique is what I would refer to as loose currying, meaning at each level of the function call, you can pass in 1 or more arguments. And the function that you get back is waiting for whatever the next argument should be. You with me? The reason why it's important to point out loose currying is because, as far as I'm aware, every JavaScript functional programming library that I have seen does loose currying, not strict currying. But if you're really trying to adhere to the true notion of what currying was as it was conceived in Haskell, you'd be doing strict currying. I think the reason why those libraries chose the loose currying form is for convenience only, not because it's the more canonically correct way of doing it. So just be aware when you see something like line 10 where multiple inputs are being passed, that still might be currying. It might just be loose currying instead.
Why does partial applications still exist in functional programming?
That's a good question. So the question is why, if currying is generally preferred, and you will find that it usually is, why even have a partial application? The best answer I can give you, other than the fact that it's sort of historical, and once something is in the canonical body of work, it's never going to get removed. Other than that, I would say there are some cases where it would be more convenient to do partial application than currying. For example, let's say you have a function that starts out expecting 5 inputs, and you want to produce another function that expects 3 inputs. You want to preset only 2 of them. If you were to curry it, 2 things would be true. First of all, you'd have to call it twice, and that's a little annoying. But secondly, the function you'd get back would not be a function that was expecting 3 inputs. It would be a curried function of 3 more chains. And that might not be the shape of function that you want to pass around. So it might be the case that a partial application produces a more preferable shape. That's not going to be common, but that's why it might still exist, is that sometimes that tool might produce a a function shape that is more preferable than a curried function. All right, remember the idea of, we did this add function before, and remember this idea of binary functions taking two inputs. What if I wanted to, say, do a map call? I know we haven't talked about map, but many of you are familiar with the idea of map, where it calls a function against several different values. If I wanted to add 1 to all of the values in my list, I could take this add 1 wrapper function and call it, pre-specifying the number 1, line 4, pre-specifying the number 1 as one of the inputs to this general add utility. Why do I have to do it that way? Why couldn't I just pass add as my mapper function?
You're calling a function off of the array.
Right, map is going to take whatever function you provide to it, and it's going to call it with each value in the array. So it's going to call it, 5 times here. But why would it not be appropriate for me to pass add on line 3 instead of this function that I've called add1? Why couldn't I just pass in add?
They have a different number of arguments.
They have a different shape. Do you see the shape? Add is a binary function. Mapper functions are expecting unary functions. A single value is getting passed in. It's the wrong shape. So what are we doing with add1 here? Fundamentally, we're changing the shape, right? And how are we changing the shape? By specializing it, by pre-specifying one of the inputs. In this case, the first input to the number 1. So you can probably guess where I'm going with this. It might be better to have a curried version of add, so that I can call line 10 add of 1 that makes my more specialized function that is the correct shape. This is an extremely common technique in functional programming. You will see this hundreds of times a day when you get into functional programming. Calling these little functions that are curried, providing one input, you get back a unary function and you pass that into like a mapper or a composition or anything like that. You will see this all over the place. So this is why currying ends up being the far more preferred form, because you could have done it with partial application, but it would have been a little bit more awkward here. It's nice if the add function is just automatically curried, and anywhere that I need to make the specialized function, I just call that with one input.
Where is the curry function defined?
It would be provided by a functional programming library. I'm not showing you the implementation of it. It's a little bit complex. I'm not showing the implementation of curry, but it would be a functional programming library's API. You call like ramda.curry or r.curry.
So what you're saying is that currying is often used to sometimes call a library that is already available for the programmer?
I would characterize it this way. So one use case for currying is that specialization. But another offshoot of the idea of specialization is that you're changing shape. And that means that in places where, for example, I have a binary function that I need a unary function, that a currying specialization is sometimes the right tool for that job. So currying allows you to take an existing function that has one shape and specialize it, producing a new function that is more specialized with a different shape that has the shape that you want.
That to me was quite interesting of all of this, because now we're starting to understand what this stuff is all about. Currying, partial application, which is a special technique, which is a specialization technique based on this generalization and specialization idea of functional programming. Why is that important? Because if you have a pure function that has, of course, referential transparency, aka anytime that whenever you call a function that is pure, the returning output can be replaced. So you can replace the returning output at any point in your application without altering the state of the app. So with that, all right, and also that how can we create this particularly functions purity, all right, that is, hey, we need to receive an input and an output, and those input and output must have a relationship. Not only that those input can be those input must be indirect, so those input can be direct, and the input and the output must be direct. Okay, if they're not, try to not reassign those inputs so you can avoid any side effects, unintended consequence, of your program, and also that you have now the single, you have for every input you have the same output, and also that if you want to, for example, is close over variables, which is something that I mentioned, here, okay? If you want to close over variables, again, don't close over variables that change its state. So with that, you cannot have certainty that the function that you write or any other author that wrote that function that follow those principles, it won't alter the state of the application. And if you need a specialization from that function, you can get that using a partial application or an occurring technique. So a partial application is just a fancy way to say, hey, I'm gonna preset the arguments right now, something that I mentioned or that I put in here, okay? So you're gonna partially apply some of the inputs now and receive the inputs later, and receive the rest of the inputs later, right? This may be something that you might use to or that you might need to. The other is currying. So for example, it's like, okay, I'm going to transform the function to take all of those inputs as a sequence of functions, where each function takes a single argument. So why this is important? Because once I know this particular techniques, the currying and the partial applications, in the currying and the partial application and currying comparison, is because this is a very interesting question. Why do we even care about partial application if we have currying? Okay, makes a lot of sense. Well, perhaps, partial application can be used in a way that give you is the proper shape of the function as an they can give you the proper shape of the function, or can redefine, So partial application can be used in a way that can be used in a way to redefine the shape of the function. So the number, the order, which is important, and here is this, okay? The number, the order, and the shape of arguments. So so partial application can be used in a way to redefine the shape of a function, the number, the order, and the shape of arguments that another function receives, or arguments that another function receives, or we return. And again, all of this receive or returns. Interesting. Okay, and that makes a lot of sense. Okay. Okay. So this is all about this. So anytime that you need a function, you need to reuse somebody else's function, and that function is now has a referential transparency, which is a fancy way to say is that, hey, that function that I need to use, it is a pure function. In other words, wherever it returned that, I can use that value, replace that in any place in our program without altering the state of the app. If that it is, so you now have certainty, which is what you want at the end of the day. Holy moly, bro. That's quite powerful and fantastic. Powerful and fantastic, bro. Oh my God. Oh, crap. Okay, makes sense.
By pre-specifying.
So, for example, like this. So, in this example, all right. So in this example, function add blah 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 blah. In this example, in line 4, we use a partial application to fit the shape of the input to fit the shape of map function. That's what we're doing here. So in line 4, we use a partial application to fit the shape of the map function. And this is what it is, man. So you're using, so for some reason you're using this map. You want to know what is the shape of this function, and then you want to return something that is accepted for this. Holy moly.
One of the inputs. In this case, the first input to the number 1. So you can probably guess where I'm going with this. It might be better to have a curried version of add, so that I can call line 10 add of 1 that.
So it might be better to have a curry function for that, which is transforming this function add into one single input. All right.
It makes my more specialized function that is the correct shape. This is an extremely common technique in functional programming. You will see this hundreds of times a day when you get into functional programming. Calling these little functions that are curried, providing one input, you get back a unary function and you pass that into like a mapper or a composition.
So this is an extremely.
This is why currying ends up being the far more preferred form, because you could have done it with partial application, but it would have been a little bit more awkward. It's nice if the add function is just automatically curried, and anywhere that I need to make the specialized function, I just call that with one input.
Where is the curry programmer?
I would offshoot of the idea of specialization is that you're changing shape. And that means that in places where, for example, I have a binary function that I need a unary function, that a currying specialization is sometimes the right tool for that job. So currying allows you to take an existing function that has one shape and specialize it, producing a new function that is more specialized with a different shape that has the shape that you want. All right, let's talk about composition. We briefly mentioned this one earlier as well when we were talking about point free. Let's dig into composition. Let's understand the idea of one function's output becoming the input to another function. Here's an example. I've got 3 unary functions, a -2, a triple, and an increment. And they do exactly what you would expect. -2 subtracts 2, triple triples it, increment increments by 1. On line 6, I'm going to call increment with 4, because that's my base shipping rate that I'm going to start with, or that's one of my base inputs for calculating a shipping rate. And then that gives me a temporary variable, and then I'm going to pass that value, line 7, into the triple function. So I went from 4 to 5, and then I passed 5 into triple, which triples it. That becomes 15, and I save that into temp. And finally, I pass that 15 value into the -2 function, line 8, and that gives me the end result, which would have been my shipping rate being added to the total cost of this product. Okay? This is a scenario that we're going to use over the next several slides to try to illustrate the idea of composition. And what you need to get out of this, the takeaway that you should be looking for, is becoming familiar enough with this pattern that you spot when one function call is producing an output that is then later routed.
This is the
to another
pattern that I
function
need
call.
to spot.
It is often the case that it'll end up in some kind of variable, and then that variable gets passed. Sometimes you'll see it literally written with them nested, like one call inside of another. But more often you'll see them assigned to variables, sometimes like temporary variables like you see here. And you want to get to the point where you can recognize, aha, that's a composition. Okay? That's the takeaway. That's the final summary. Okay? So what I'm going to do to illustrate composition for you is I'm going to ask you to switch your brain between the code scenario that we're looking at here, and I'm going to ask you to look at a metaphor that I'm going to use to describe it. Okay? As we talk about this metaphor, the first step that I want to address is this idea of abstraction. How many of you have heard that term before, abstraction? Okay? Abstraction is one of those terms that is thrown around in programming, and nobody really can pinpoint and say definitely this is what I mean by abstraction. It seems to have lots of different meanings in lots of different places. But I want to talk about the original idea behind abstraction. The original idea behind abstraction is that you have two or more things in, say, a piece of code that are intertwined together. We could look at lines 6, 7, and 8, and we could say that there are two distinct concepts happening here, and they're interwoven. One of the concepts is that we're calculating a shipping rate, and one of the concepts is that we're adding that shipping rate to the base total for this order.
So the data and the
Those are two
functionality.
distinct concerns, but in this particular piece of code, they're wrapped up together. Okay? The original idea of abstraction was to tease apart two things which were otherwise intertwined together. To tease those two things apart so that they are separate, and by way of separation, we insert in between them a semantic boundary that allows us not to hide one or the other. That's what a lot of people think abstraction is about, hiding. It's not about hiding. It's about separating. Abstraction is saying, take these two things, separate them, so that I can look at this thing and understand it, or look at this thing and understand it, without, while looking at this thing, having to worry about this one, or vice versa. By separating them, we make them easier to understand, easier to analyze. So how would we abstract lines 6, 7, and 8? Not hide things, but rather separate things. That's what I want you to keep in the back of your mind as we go throughout this discussion. Okay? So the metaphor I'm going to use, and we're going to be mentally jumping back and forth. So hopefully you've had your caffeine. Hopefully you're ready to mentally jump back and forth between these two scenarios. For this scenario, I'm going to ask you to play as if you are an engineer at a candy factory. Okay? And at the candy factory, you have these machine setups like you see here. You got these machines with conveyor belts in between them where they produce the candy step by step by step down the assembly line. Okay? So on the far right here, we see a machine that, you see my great art skills. I'm a pretty good artist here. You see this machine that takes melted chocolate, you pour in the melted chocolate, and what comes out on the bottom is these cooled blocks of chocolate. Okay? That's what machine 1 does. Those cooled blocks of chocolate rumble down the conveyor belt to the left. They go into the next machine whose job is to chop it up into tiny little pieces. And so those tiny little pieces are coming out of that machine. They rumble down to another conveyor belt, and they fall into the third machine, whose job is to wrap them up in the nice candy wrappers.
Line.
And those roll along the next machine.
An assembly line that anytime they pass
so
through
in this candy factory, we've got a couple of these
input,
contraptions, if you will, these machines set
an
up on the
input, an
factory
output,
floor,
an input,
and everything's
an
going well. You're the engineer who's responsible for managing all these machines. One day, the CEO, the owner of this, president or whatever, of this candy factory, comes to you and says, hey, you've been doing a really great job, but we've got a little bit of a problem, and I want to see if you can think about how we could fix this problem. Okay? Because he says, the problem that we have is that our competitors are producing a lot more chocolate more quickly than we are. Like they're producing 3 or 4 times as much chocolate every day as we are, and we're losing to them, and we got to figure out a way to catch up. We need some way to catch up. So the boss is basically saying, can you figure out some way for us to make more chocolates? Now, you know that these machines can't be sped up. We can't, make them run faster. So the only way to make more chocolates is to have more machines. We're going to have more of these set up. And the problem is we don't have room on the factory floor. They're taking up so much space. We only have room for a couple of these in the factory. So you begin to roll around in the back of your head thinking, how could I make more room on the factory floor for more of these machines so that I could make more candy and we could keep up with our competitors? That's what you're going to be thinking as an engineer at this candy factory. Now I want to press pause on that scenario.
Exactly.
And I want us to go back to that code snippet that we were just looking at. Remember the code snippet where I had those temp variables, okay? Those temp variables are kind of cluttering things up, and they're not really benefiting us anywhere very much. And so we think, you know what, let's just get rid of the temp variables, and let's just have each function call nested inside of another function call. Call increment 4, and then pass that to triple, and pass that to -2, and then bam, we've calculated the shipping rate. Anybody ever done this before? Have you ever nested function calls like that before? Okay. So whether you knew it or not, you were doing composition. That's a function composition, taking the output of one function, making it the
Taking
input
the
of another.
output of the function.
We got rid of those messy,
make
ugly
it
temp
the
variables
input
that were
of another
taking
one.
up too much
Take
space.
the output of that function
in
and
our
make it an
program.
input of that.
You with me? And we've cleaned up the code. Let's go back to the candy factory. You're the engineer and you've been thinking to yourself, you know, I think what we ought to do, I think the big problem is that those conveyor belts are taking up too much space. So you get this brilliant idea one day. You say, what if I just took out all the conveyor belts, and what if I just stacked the machines right on top of each other? And I've got one machine at the very top where we pour in the chocolate. The chocolate falls out of that machine directly into the next one. It falls out of that machine directly into the next one, and so on. And bam, problem solved, because now I can install many, many more of these on the factory floor because I got rid of all that unnecessary clutter of all those conveyor belts, all those temporary variables. You with me? So you install this solution in the candy factory, and all of a sudden the factory starts producing more candy, and everybody seems happy, and the boss slaps you on the back and says, great job. Things go well for 6 months. And then one day the boss comes to you and says, hey, we've got another problem. I need to see if you can try to solve for us. We like the fact that we were able to produce more candy, but one of the problems with this new solution that you came up with, our factory, the line workers, they've been complaining because these machines being stacked on top of each other, it's very cluttered. Like there's wires all over the place, and they have to remember to push the button at exactly the right time, and there's too many buttons to push and too many wires. Is there some way that you could just make a single machine that they pour in the chocolate and out comes the wrapped candy? That's what the boss says, right? You know, because bosses, they don't think in terms of reality. They just say, you know, you engineer, go make it happen, okay?
You engineer,
So he's basically
go
asking
make
you
it
to
happen.
invent some kind of machine that does it all in one. Takes the cool chocolate, the melted chocolate at the top and spits out wrapped candies. Make it easier for all the factory workers. And you're thinking to yourself, well, even if I could do that, it would be difficult for me to maintain each of those individual steps and pieces. I'm going to have some way to access what's going on, right? So this is what's rolling around in the back of your head. You're the engineer, you're trying to figure this stuff out. We have the same problem back in our code base, which is that we've got the place where we're calculating our shipping, and then we've got the place where we're adding that to the total. And these two things are all wired up. It's hard to reason about each one independently. So you think to yourself, I know I'm a good engineer. I know what I need to do. What I need to do is write a function. Make a function called shipping rate, which does that work. It does -2, triple, and increment. It takes in the value. And now look at line 12. Line 12 is much cleaner because line 12 is semantically separated the two concerns. Line 6 is where we calculate how to do, where we say how to do the shipping rate calculation. And line 12 is where we say what to do with it, which is to add it into the order. This is called an abstraction. And the semantic boundary that we inserted is the function name. The function name shipping
It's a
rate
semantic name
is the
here.
semantic boundary between how to compute the shipping rate and what to do with the
What to
shipping
do.
rate. Those are the two separate concerns that previously were all intertwined together, but because we made a function, now they're nicely semantically separated. So back to the candy factory. You've been thinking about this for a while, and you think you've come up with a brilliant solution. I don't need to change anything about the machines. All I need to do is wrap one nice little clean box around the whole setup. Just make one nice big box that's wrapped all the way around all those internal machines. And on the inside, there'll be a nice access panel where I can open it up and get at all the machines and wires and buttons if I, the engineer, need to work with it. But the factory workers just have one on-off switch. They have one input valve at the top where they pour stuff in, and out from the bottom comes the candy, wrapped and nice, ready to go. And you're thinking to yourself, this is the best of both worlds, because the factory workers only care about input and output. But I, the engineer, I care about how it gets done. What have I done? I've created an abstraction for my composition. Right? I've wrapped it in a function. That's what this big box is conceptually. You implement this solution, and then you get some feedback from the boss. He says, oh, the factory workers love it. They think it's great. Every day they're coming in, they're telling us how easy it is to push the buttons, and our other maintenance engineers can open up the access panel whenever they need, and it's all nice and great job, great solution. 6 months go by, everything's been humming along nicely, and the boss comes up to you one day and says, I got another problem I need you to solve. This is a very needy boss, right? Got a lot of problems for you to solve.
It's a very needed job.
All right, so this has got another job for you to solve. Another problem.
We got a job security.
Another problem I need you to solve. This is a very needy boss, right? Got a lot of problems for you to solve. That's good job security, man. All right, so this has got another job for you to solve. Another problem. You see, what we've noticed is that our competitors are able to come up with new kinds of candy almost on a daily basis. They try out one kind of candy one day, and the next day they're producing an entirely different kind of candy. It's amazing how quickly they can just spin out new kinds of candy, and we're not able to keep up with all the different kind of experimentation that they're doing. We just only produce the one kind of candy over and over again. And we've tried, we've experimented, but it's too slow to make these single boxes with all these machines configured. Can you come up with some way for us to do this more efficiently? For us to make these machines that make our candy for us, but we want to make them more efficiently. Without even realizing it, the boss is asking you the most ludicrous thing of all. He's saying, could you make me a machine that makes machines? A machine that takes machines as inputs and outputs other machines. Could you make me something like that? Go invent it. This is a real head scratcher. It's going to take a while to try to invent, okay? But you'll work on it. Let's switch back to the code. We've been thinking about that shipping rate calculation, and it's been going along fine. And then somebody else in the company says, we actually have different kinds of shipping rates. We have like international shipping rate, we have domestic shipping rate, we have like express shipping rate and overnight shipping rate. We need to, but everywhere we keep defining all these different functions is cluttering up our code. Could you make it easier for us to define these shipping rate functions? So you, the programmer, think, well, sure. Because there's a pattern involved in defining each of these functions, which is that each of the shipping rate functions takes a different set of 3 functions and calls them in succession. So you think to yourself, I'll just make myself a utility. And maybe I'll call this compose 3. It takes 3 functions, fn3, fn2, and fn1. I'll explain why that ordering in just a moment. It takes those 3 functions, and it puts in the next. You might say the international shipping rate, and instead of saying -2, you say -1, and instead of saying triple, you say quadruple, and you just pass in different functions, and you get a different shipping rate function as a result.
So that'll be all for this video. Take care. Bye-bye.